So let's start to think about what happens in the broadest sense of exercise in terms of cardiovascular responses. Well, fairly simple. If we're going to perform physical work or we're going to do exercise, you've got to increase delivery and use of oxygen, because we are by definition aerobic. And even when we're doing low intensity exercise, even going for a walk, there is an increased demand at the muscle to do work. The muscle is going to lengthen and shorten. In order for the muscle to lengthen and shorten, we need to provide the cell with the correct conditions in order for that to work, and that is to have an oxygen-rich environment. In order for that to happen, because of what we've seen with the Fick equation, the QO2 at the muscle will go up, because the muscle needs to do more work. It's got to lengthen and shorten more forcefully. If it's going to lengthen and shorten more forcefully, there will be an increase in QO2. If there's an increase in QO2, the feedback will be that there'll be an increase in VO2, because we've got to extract more oxygen from the atmospheric air to meet the QO2 at the muscle. In order to do that, one key component is we've got to deliver more oxygen to the cell, so we know that cardiac output is going to rise. So, just to reinforce it, the amount of oxygen utilised, that's our VO2, depends on the amount of physical work performed. That's the exercise intensity, and that is really going to relate to the amount of work the muscles need to do, the amount of force they need to generate, the number of contractions that need to be produced, and that, as we've already dealt with, is expressed by the Fick principle. So VO2 equals cardiac output times a VO2 difference. So if we go by extension slightly further, the amount of oxygen consumed by any individual at maximal exercise is termed VO2 max. And VO2 max is influenced by age, gender, exercise habits, genetics, and even health. We'll deal with those in a moment. But just to summarise that, if we have the idea of VO2 equals Q times A VO2 diff, I think it's fairly easy to understand that if we're referring to VO2 max, which is the maximum amount of oxygen that we can consume, that must mean that the maximum amount we can deliver has been achieved. Now that can only happen if we reach maximal cardiac output and we have maximal extraction. So VO2 max, using the Fick equation, VO2 max equals Q max times A VO2 diff max. Now, how is VO2 max influenced by age? Well, we know that we start to get quite significant decrements in VO2 max beyond about the age of 21. And we look at about a 1 to 2% decrease in VO2 max per decade beyond the age of 21. We know that males have higher VO2 maxes than females, proportional in relation to age and training status. And that's primarily because males have a larger muscle mass, they have a bigger pumping capacity of the heart, and carry more hemoglobin and red blood cells. So the VO2 max in males is higher. We know that what we do in terms of exercise will increase the VO2 max. So we know that people who are trained individuals will have a higher VO2 max than those individuals who are untrained. We know that, for example, certain types of training will boost the VO2 max more than others. So, for example, a sprinter will have a relatively low VO2 max in the pantheon of individuals who are trained, compared to a marathon runner or, for example, a cross-country skier who will have exceedingly high VO2 maxes. We know that VO2 max is genetically limited, so about 45% of the VO2 max is set genetically. So we've actually only got about 55% which we can work with. And the degree to which your VO2 max changes is a function of the genotype that you inherit. And finally, we know that VO2 max and therefore oxygen consumption is limited or affected by health status. So it's not surprisingly, given the Fick principle, VO2 max decreases if we've got cardiovascular disease. It decreases also if we've got issues relating to the respiratory system, and also if we've got issues relating to muscle and neuromuscular physiology. So VO2 max is very useful in that sense because it perhaps allows us to categorise people for age, for exercise habits, and for health status as well. So let's just think about what is happening during a VO2 max profile. So here we've got percentage of VO2 max on the x-axis, and then on the y-axis, the double y-axis, you can see we've got cardiac output on the left, and on the right we've got our stroke volume response. And you can see heart rate are the squares, cardiac output are the diamonds, and the stroke volume are the triangles. Now, what you can see are a couple of really important things. The first thing to notice is that the cardiac output in this diagram shows a pretty uniform response with exercise intensity. In fact, you would describe that response as near as, damn it, linear. There is a slight inflection when we get to about 70% of VO2 max, but it's pretty linear response. Almost as linear as the response you see for heart rate. So you can see that as the exercise intensity goes up, there is a uniform response for the heart rate. It's almost a perfect line. But notice that the response for stroke volume is non-uniform, and in fact what you see is quite jagged responses. It goes up quite significantly at about 20 to 25%, then it levels out to about 75% VO2 max in this instance, and then rises again. And so, bearing in mind that cardiac output is a function of heart rate and stroke volume, the fact that heart rate the fact that cardiac output is showing this fairly linear response, but stroke volume is leveling out, you can see that the driving factor for the cardiac output has to be that continual rise in heart rate. Now, these aren't just standard uniform responses. This is a schematic from a single study, but it gives us an idea that there is a uniform like response, particularly for heart rate in response to exercise intensity, and that the cardiac output actually follows, as we'll see later on, follows the response for VO2. Perhaps the rogue variable, and we'll deal with this in more detail, is the stroke volume. The stroke volume does not follow a traditional response. It's not a linear like response to exercise intensity.